So now that we've talked about what the solutions look like and how to determine if something is a solution, let's talk about how to actually find the solutions. So before I actually show you using matrices, which is the way we'll be doing throughout the rest of the course, let's do a modification on the elimination method, just to kind of give you some background on where this method comes from. So I have this system of equations. So to start with, I'm going to multiply the first equation by -2. So -2 times equation 1. That gives me -2x minus 2y is equal to -10. I'm then going to add this to the second equation. And we do this to make things cancel nicely. -2x plus 2x is 0. -2 minus 3, that gives me a -5y equal to -10. So now I have a new system of equations. I have x plus y equal to 5, and I have 0x minus 5y is equal to -10, since that's what this last step just gave me. We can go ahead and change that, leave the first equation alone, and then just divide the second one by -5, just to make the coefficient of the y a 1. At this point, you could probably solve this equation, but we're going to do a little bit extra first. I'm going to do a negative times the second equation. So that's -0x minus y equal to -2. And then I'm going to add that to the first equation, which is x plus y equal to 5. This time, my x's cancel. -0 plus 1 is going to be x. And then -2 plus 5 is 3. So now my new equations are x plus 0y equal to 3 and 0x plus y equal to 2, which gives us the solution 3, 2. And I know normally you wouldn't write 0x or 0y, but like I said, that's going to be helpful whenever I move these to matrices, just to kind of understand exactly what's going on. So I've been saying I was going to move these to matrices, but you may be wondering, what exactly is a matrix? Well, a matrix is just a rectangular array of numbers. And in particular, I'm going to be concerned with two. The first one is going to be the coefficient matrix. So my last example said x plus y equal to 5, and 2x minus 3y equal to 0. So the coefficient matrix comes from just listing off the coefficients. So the first equation has a 1x and a 1y. The second equation has a 2x and a minus 3y. And that's it. So you'll notice when I do this, every row corresponds to an equation. This is the first equation. This second row is the second equation. And every column corresponded to a variable. These right here are the coefficients of x, and the second column is the coefficient of y. We also have what's called the augmented matrix. And the augmented matrix is the one that's actually going to be used the most often whenever we're actually solving these systems of equations. It comes from first writing down the coefficient matrix, and then we're going to add a column which consists of these constant terms, 5 and 0. Oftentimes you'll see a bar in between the coefficient matrix and the augmented column, and that just represents an equal sign. It lets you distinguish which part of the coefficients and which part of the constants that it should be set equal to. When working in the previous example, we had three main things we could do. We could add a multiple of one equation to another equation, which we did twice. We could multiply one equation by a non-zero constant. That was actually the second step in that solution. The third thing we could have done was interchange the equations. In that last example, that wasn't necessary, but it could be just for various reasons to make things a little bit easier. It basically says the order I wrote the equations down in doesn't matter. However, when we're dealing with matrices, these three operations become elementary row operations. So the first is replacement. We're going to replace one row with the sum of itself and the multiple of another row. So I represent this by multiplying one row by a constant c and adding it to another row. I tend to write it in this method, where this row right here, this r sub j, is the one being replaced, just to make it a little bit easier to have some kind of convention or norm. The second thing you can do is multiply all entries of a row by a non-zero constant. That corresponds to multiplying an equation by a constant. And I'll represent this just by CRI. The third thing is to interchange two rows. Like I said, the order the equations are written down doesn't matter. So if I wanted to switch the order, that would be equivalent to switching rows. And that's denoted with this double arrow. So these are just shorthands so that it'll be a little bit easier to distinguish. And overall, what we're doing is we want to use these row operations to turn that augmented matrix into something that looks like this. Because now we could pull the equations directly out. We would have x plus 0y equal to 3, 0x plus y equal to 2, which is what we had previously. It's just a matter of the fact that this one is a lot easier to read the solution out of. So this form that I want the matrix to be in is called reduced row echelon form. So let's actually define that. We say a matrix is in row echelon if we have these three properties. 1, all non-zero rows are above any zero rows. And a non-zero row is just a row in which at least one entry is not zero. The first non-zero entry in each row is in a column to the right of the first non-zero entry of the row above it. So the first non-zero entry is known as a leading entry or a pivot, and it's basically saying these pivots should stair-step down and to the right. 3, all entries in a column below a pivot are 0. So if I just deal with row echelon form first, let's give a few examples of these properties. So 1, I could do 1, 3, 4, 0, 9, 0, 0, 7, 5, 4, and 0, 0, 0, 2, 0. So the first thing to note here is that we don't have a row of zeros. Therefore, the first property is automatically satisfied. The second one, the first non-zero entry in each row, is in a column to the right of the first non-zero entry in the row above it. So I want to look at the pivots. This is the first non-zero entry in the first row, the first non-zero entry in the second, and then in the third. And the idea here is that as we move down, we should also be moving to the right. Down and to the right. And that is satisfied. We also need everything underneath these pivots to be zeros. And we can see that they are. So this one, row echelon form. Another example. 1, 0, 0, 9, 1, 0, 2, 7, 1. So once again, there's no row of zeros. My pivots are moving down and to the right, and everything below those pivots is a 0. One last example. 2, 0, 0, 7, 0, 0, 4, 2, and 0, 0, 0, 0. So this time I do have a row of zeros. And the important thing here is to notice that it is at the bottom. My pivots do move down and to the right, and everything below those pivots are zeros. So to be in reduced row echelon form, we need those three properties, along with two more. That first non-zero entry in each row should be a 1, so my pivot, or leading entry, should be a 1 in each row. And then the last thing, all entries in a column above a pivot are also a 0. So not only do the entries below the pivot have to be 0, but above it must also be a 0. So for example, if I want to do things in reduced row echelon form, here are a few examples. The first one, 1 0 0 0 1 0 0 0 1. So this one, there's no row of zeros. My pivots do move down and to the right. Everything above and below those pivots are a 0, and each of those pivots are a 1. This one right here is actually a special matrix called the identity matrix, and we'll actually talk more about that a little bit later. Another example, 1 0 5 8 0 0 1 2 4 0 0 0 0 0 1 and then 0 0 0 0 0. Once again, pivots are moving down and to the right. The row of zeros is at the bottom. Everything above and below the pivots are a 0, and each of those leading entries is a 1. One last example. 0 0 1 0 0 0 0 1 and then 0 0 0 0. So this also satisfies all 5 of the properties. So now that we've done that, let's do some non-examples. Examples of matrices that are in neither reduced row echelon form or row echelon form. So one example, 4 5 1 9 0 0 0 0 0 0 2 0. So this one, you'll notice the row of zeros is not at the bottom, so it's in neither of the forms. Another example, 1 0 9 4 0 0 2 5 0 1 0 0. So these pivots don't move down and to the right. For example, I have this 2 and this 1, so that moves down and to the left, which causes a problem. One last example, 8 0 4 9 0 9 2 4 0 1 3 7. Here we can see a pivot in the second column, but the stuff below it is not a 0, so it fails to satisfy the properties. So it's important to note that there are many possible different row echelon forms of a matrix. However, each matrix only has one reduced row echelon form. So I can get it into many different row echelon forms, but if I want to go all the way down to reduced row echelon form, it will always have the same result, provided I start with the same matrix. So let's do an example. We want to consider a 3 by 3 matrix, so 3 rows and 3 columns. And I want to give all the reduced row echelon forms. I'm going to use a square to represent non-zero numbers and a star to represent any number, including 0. So when we do this, let's start by thinking how many rows of zeros. Well, we could have 2 rows of zeros. We can't have 3 because I said a non-zero matrix. So if we have 2 rows, the pivot has to be in the first row. It could be in this first row, first column, in which case the other entries in that row could be anything they wanted. And then the zeros underneath it. Another possibility would be to have the bottom 2 rows of zeros. And then we could have the pivot in the second column. That means the first entry is a 0, and the third entry can be anything. The third and final possibility, when we have 2 rows of zeros, would be to put the pivot in the third column, in which case everything before it should be a 0. We could have also had one row of zeros. In this case, let's think about where the pivot is. Well, now I have to have two pivots, one in the first row, one in the second. So I could do the first and the second columns. So everything above and below those should be a 0, and the other entries won't matter. I could also have a pivot in the first column and the third column, in which case I have zeros before that one, I have zeros above that pivot, and then this entry could be anything. The third possibility would be to have pivots in the second and third columns. So, that would put zeros underneath and above those pivots. The last possibility would to have 0 rows of zeros, in which case I have to have a pivot in every row and every column. So it would look like this.